Most of us click Join Meeting without giving it a second thought. But behind that one little button is an engineering marvel of just incredible scale. So today, we're going to deconstruct Microsoft Teams and really get into how it's even possible to connect hundreds of millions of people pretty seamlessly every single day. And to really wrap your head around the challenge here, we have to start with this number, 300 million. That's how many people use Teams every single day. Just try to picture that. It's like the entire population of the United States and then some, all working together in one digital space. The scale is just mind-boggling. So that brings us to the real question, right? How in the world do you build a system that can handle that kind of pressure? And it's not just about making sure it doesn't crash. It's about delivering a perfect experience. And that is one of the biggest challenges in software engineering today, for sure. To answer that question, we first have to understand the core demands. This isn't just about having a lot of users. It's about making some really specific, concrete promises to every single one of them. Yeah, these aren't just goals on a whiteboard. They are totally non-negotiable. Low latency means your message has to get from you to your coworker in under 200 milliseconds. That's literally faster than you can blink. And high availability of 99.99%, well, that means the entire service can't be down for more than 52 minutes in an entire year, and it all has to be locked down with enterprise-grade security and work even if parts of the network fail across the globe. The bar is just incredibly high. So with a list of demands like that, where do you even begin? Well, you start with a high-level plan, a blueprint that helps you organize all that chaos. At the very highest level, the whole architecture has three main layers. First, you've got the clients. That's just the app running on your phone or your computer. Your app talks to load balancers, which are kind of like air traffic controllers for data, directing all the requests. And all that traffic gets handled by the real powerhouse of the system, the backend. But the backend isn't just one giant program. Oh no, it's much smarter to think of it like a bustling city of specialized services, what engineers call microservices. Each one has a very specific job to do. One handles logging you in, another just manages chat messages, and another is completely dedicated to video calls. This whole approach is absolutely fundamental to how Teams manages so much complexity on a global scale. Now, before you can use any of those services, you have to get past the main gatekeeper, Azure Active Directory, or AAD. When you log in, AAD is what confirms you are who you say you are, and then it hands you a secure digital key called a token. Think of that token as your passport for the rest of the system. It proves to every other service that you're allowed to be there. This is really the bedrock of Teams security. Okay, so now that we have the blueprint, let's actually trace the journey of a single chat message to see how all these pieces work together. What really happens in that split second after you hit send? So the moment you hit send, your app shoots that message over to the chat service. That service immediately stores a copy in a database, just to be safe. And then the real magic happens, a process called fan-out. This service figures out every single person who needs to get that message and pushes it out to all of their devices. We're talking phones, laptops, everything, all in a fraction of a second. But what about that little green dot next to your profile picture that shows you're available? It seems so simple, but the system has to track the status of 300 million people in real time and share it instantly. How does it do that without just completely grinding to a halt? The answer is a really clever piece of tech called the presence service. See, instead of writing every single status change down to a relatively slow database, it keeps all of this information right in the computer's main memory. Think of it like a super fast cache. This is what allows it to handle millions of updates every second, making sure that status indicator is always up to date. Okay, so chat and presence, that's one thing. But streaming real-time video and audio, that is a whole different level of complexity. So let's look at how a Teams call actually works under the hood. It all starts with a technology called WebRTC. It's this amazing open source standard that's built into basically every modern web browser. It's the magic that lets us have real-time video and audio chats without needing to install any weird plugins or special software. Now, for a simple one-on-one call, a direct connection is fine. But what about when you have, say, 10 people in a meeting? If you used a simple mesh network, your computer would have to send its video stream to 9 other people and receive 9 streams back at the same time. Your internet connection would just melt. It would be a disaster. That's why Teams uses a much smarter approach, something called a Selective Forwarding Unit, or SFU. With an SFU, your computer only sends one single stream up to a powerful central server. Then, that server acts like a smart traffic cop. It takes your one stream and efficiently forwards it to everybody else in the meeting. Your computer only has to do the work of sending one stream, not 9. And this, right here, is the critical design choice that allows Teams meetings to scale up to hundreds of people. As we've been seeing, building a system like Teams isn't really about finding these perfect, magical solutions. It's about making smart choices and understanding the trade-offs. And that is a core principle of great engineering. And this gets right to the heart of what makes system design so tough. There's almost never a single best answer. It's always about weighing the pros and cons of every decision. Things like, do you choose speed over perfect consistency or scalability over simplicity? Let's look at the key trade-offs they made. For chat, they chose eventual consistency. Now that sounds fancy, but it just means they prioritize speed and availability over the guarantee that every single person in the world sees the exact same data at the exact same millisecond. They decided that a tiny delay is acceptable if it makes the whole system feel instant. Pretty smart. And for video, they chose that more complex SFU model because having huge meetings was way more important than having a simple architecture. Every decision is a calculated compromise to hit a bigger goal. So, if you only take away a few key ideas from all this, let it be these. First, the chat fan-out pattern for getting messages to tons of people efficiently. Second, the SFU design for making video calls that can actually scale. And third, the importance of a central identity system like Azure AD. These aren't just Teams features. They are fundamental building blocks for any huge real-time app. This incredible engineering foundation opens up so many exciting possibilities for the future. We're already seeing AI that can summarize your meetings for you. But what's next? Could a system like this eventually predict when you'll be available just by looking at your calendar and your chats? When the foundation is this strong, the future applications are almost limitless. So I'll leave you with this. What do you think is the next big leap?